So for those of you who are absent, this would be a good video to watch. So this video goes over, so again, if you weren't here, you want to watch this video. This video is going to go over the reactivity of group 1, so your alkali metals. So just a good thing to watch so you kind of understand when I'm referencing things that you know what we're talking about for that. So we looked at in the video group 1, which is lithium, sodium, potassium, rubidium, cesium, and we're going to go through why they reacted as they did. So we're going to compare the least reactive, which was lithium. So lithium in the video basically did nothing. We're going to compare it to cesium, which in the video cesium created a huge explosion. So we're going to find out why this happened. So the first thing we want to look at are the electron configurations, because in an atom, the protons plus the electrons are going to determine the chemical properties. So the protons determine the element, and then when we gain or lose electrons, their chemical properties change. Okay, and remember, they give electrons or take electrons from other atoms or to other atoms. So they don't just give them out to thin air. Lithium, if it's going to lose an electron, it's going to give one to fluorine or chlorine. So it's going to give it to another element, which is why this new reaction takes place. So lithium, we know, has 3 protons, and it has a configuration of 1s2, 2s1. Cesium, we look, has 55 protons, just so you can find them. And if we wanted to do the electron configuration, we would do xenon, and then we would do 6s1. So looking at what we know for these, we know that they both are going to have 1 valence electron. Okay, so that we know right away, 1 valence electron, because if you look, the highest energy level is 2, there's 1 electron, highest energy level is 6, 1 electron. That means in order to stabilize or to become the octet or the duet, because lithium wants to become a duet, so in order to get its full shell, they're both going to lose 1 electron. Okay, that's what they're naturally going to want to do, meaning lithium is going to form a +1, cesium also going to form a +1. But why, if they're doing the same thing, did cesium create such a large reaction where lithium hardly created any reaction? So let's look at I'll switch colors. So let's look at the orbital or the diagram. So if we were to draw lithium, I'm going to use the plus sign to represent the nucleus, because inside the nucleus are your protons and neutrons, so the nucleus overall is positive. And we're going to draw 2 rings around lithium. When we're forming a bond or a reaction, the only electrons that can be gained or lost are the valence electrons. So those are the only ones that I'm going to put on here. So I'm going to put 1 valence electron on lithium, and then I'm going to draw cesium. And cesium is going to have 6 rings, because if you look, it has 6 energy levels. So I'm going to draw lithium with 6 rings. Or 6 energy levels. So we're going to call them energy levels, meaning they're going to have 6 energy levels around the nucleus. And they're also going to have 1 electron. So both of these atoms want to lose an electron. So they want to try to find somewhere to give this electron to. So I'm going to have Mr. Fluorine atom coming along, because he has 7 valence electrons. So he's in the hunt to gain an electron. So we're going to look and see, well, who is he going to get the electron from? So atoms are pretty lazy. They're going to take the easy way out. So whatever is easiest for them, that's what they're going to do. They're not going to fight for an electron. They're going to just go and steal one with the least amount of effort possible. So we got to think about this. So we have these valence electrons here. We got to think of what's holding on to these valence electrons. Well, electrons we know are negatively charged, which means that something in the atom, positive, is holding on to the electrons. So we have to think what's positive. So if we think about it, well, we know the nucleus is positive, which means the nucleus is what's pulling on to this electron. So that's what's holding on to this electron, is that nucleus. So which one would be easier for fluorine to take from? Well, if we look, this valence electron right here is so far away from that nucleus. And this nucleus is being blocked 5 times. So this electron is being blocked from the nucleus 5 times. So this nuclear charge is not as strong because the electron is so far away and it's being shielded. So each energy level is going to produce what is called electron shielding, which basically is going to dilute the charge of the nucleus to the outside electron because each of these shells or energy levels are filled with electrons which are negatively charged. So fluorine doesn't want to take it from lithium. So remember, this is lithium over here. He doesn't want to come and take it from lithium because it's going to be harder because this nucleus is so close to that electron that it basically has a super grip on that electron. This nucleus, however, is working really hard to try to grab that electron because that electron is so far away from it. So this fluorine is going to attack the rubidium and leave the lithium alone, which is why we saw a drastic reaction because there were so many reactions taking place in that water because they were stealing so many electrons from rubidium. We actually have a term for stealing electrons or losing electrons, and that is called your ionization energy. So your ionization energy is the energy required to lose an electron. So if we look at these that we are comparing, the lithium is going to have a high ionization energy, meaning it is going to take a lot of energy of fluorine to take an electron. So this is a high ionization energy, meaning it takes a lot of energy to take an electron from it, where this is going to have a low ionization energy. Pretty easy for another atom to come and take an electron from it. Okay, so it's pretty easy for this one to lose an electron. So now we have to think of the opposite. So when fluorine, for example, is taking the electron, there's also a trend for that, and that is called your electronegativity. So keyword, so a way to remember this is when something gains an electron, it becomes negative. That's why it's called electronegativity. So it's becoming negative. So the ability to become negative. So this is going to be the ability to gain an electron. So if we're looking at the ability to gain an electron, we're going to just concentrate on lithium and cesium. So yes, naturally they don't want to gain an electron, but they're still going to have an electronegativity, meaning they're still going to have a concept relating to gaining an electron. So again, we have to focus on what's gaining this electron, what's attracting this electron. It's all going back to that nucleus because the nucleus is positively charged. So let's say in a certain circumstance that these atoms want to gain an electron instead of lose one. So now they're trying to gain an electron. Well, let's say that there is this electron floating around out here. So we'll do a gray electron. So there's this electron floating around out here. Which nucleus is going to have a better chance of gaining it? So if we look, well again, this nucleus right here, so that one in cesium is so far away from the outside. It has so many levels to get through. So let's get 1, 2, 3, 4, 5 levels to get to the electron. This nucleus only has to get through 2 energy levels. So lithium has a high electronegativity, or higher electronegativity than cesium because it's going to have a better chance of grabbing that electron, where this is going to have a low electronegativity. That nucleus is really going to have to fight for that electron. Okay, it's going to have to break through 6 electron shields to get to that electron. All right, and then our last term we talked about is atomic radius. And our atomic radius, to measure this, is half the distance between 2 nuclei. And this is just basically the size. So if we look, well, cesium is bigger, so this is going to have a larger atomic radius, mainly because, well, it has so many more energy levels. So it's a larger atomic radius, where this is going to be small. This is going to be a smaller atomic radius. So a lot less energy levels, making the size smaller. So now we can look at the same concept, but looking at group 17, which are your halogens. So we're going to go and we're going to compare fluorine versus iodine. So I want you guys to go through and do that and figure out which is going to have the highest ionization energy, electronegativity, and atomic radius.